Yes. Let's go.
For me, the first thing is chemical formula and structure, like maybe a 3D structure. Maybe we will need aggregate state, structure, and solvent as well, because they will influence in the spectrum.
Okay.
Aggregation, like aggregation state, like in which state the compound is, like because like in solid and in fluid it is different, but actually with aggregation it can be as well, but it's more to the state
Yeah.
in which compound is.
So we'll deal with the aggregation part later, but okay. What else?
You have to give the method you want to use, the calcul method you want to use.
So, in order to resolve the Schrödinger equation, you need approximation, and the computer, the program, do not have any yet any intuition. So you need to specify what kind of method and approximation. Okay. So usually by method, there is Hartree-Fock or DFT methods. Hartree-Fock or DFT methods, for example. And in DFT, you need to give the functional. Okay.
Is the functional like 631G plus
No.
D? No, it's not this.
No, it's the other one. The functional is the approximation concerning the Hamiltonian. So, what kind of interaction you take into account, and it can be functional B3 leap, PBE, and so on. So usually there are acronyms of names. Perdue, Burke and Ehrenfest, or I don't remember the E one. This one is Becquet exchange with Lee, Yang, and Parr correlation. And the method is usually associated with an approximation with the wave function. So the atomic functions, how they are described, and this is the basis set. Like 6, 3, 1, G, and so on. Okay. So now the computer knows what kind of atoms in 3 dimension, and the 3 dimension part is super important because, for example, ethane or many molecules can have for the same chemical formula different spatial conformations, so you don't know which one you're looking for. So the aggregation is in just that if it's in dimers, if you have a solid state, if you have a liquid state, if you have a solvent, okay? So we'll deal with that. For example, right now, let's put it more in the end. Up. Okay, so chemical structure, calculation parameters, and what else?
You can give information about your molecule, like his state, like singlet or triplet state. You can tell the number of charges and the geometry of your molecule.
Not only you can tell, but you must tell. Okay, so I'm trying to do a list and it's not really working great. Okay. And you give the charge, therefore it can deduce the number of electrons and spin multiplicity. One typical example is usually it's a neutral charge and a singlet state. So you give a charge of 0 and a spin multiplicity of 1. But if you do that for oxygen, you will have a strange answer. Okay? He will not compute the spin state that is the most stable of all. You need to give this information. So you choose the spin state, if it's a singlet or not. Beware, you have, for example, if you have a d radical and you want the singlet but open shell, you need to be more specific. By default, if he sees a spin state of 1, a singlet state, it will be a closed shell. That means that all alpha electrons will be with a beta electron in the same orbital.
And how can I know which spin multiplicity I have to choose?
Yeah, that's a good question. For organic compounds, if it's a radical, you know that you will have, for example, one free electron, so it will be a doublet. For closed shell in your compound, if you have a Lewis or developed structure where all electrons are paired, you will start with a singlet, unless you know, for example, that the deoxygen, you know that you have a triplet state and you have an experimental proof of your spin state. Statistically, you have more than 95% of the organic compounds that are singlets. But if you do some inorganic compounds, and you can talk about it with George, you need to think about your spin multiplicity depending in your metal environment. Is it a weak force field or not, a ligand field, and what will be the most favored spin multiplicity? So we have a 3D structure.
I have a complex like of zinc with organic ligands.
Zinc, usually if you have zinc, so you have a full D shell. So usually it's a singlet state. You don't have paramagnetism with zinc compounds. If you have a typical coordination for zinc. So we start like that, and we'll see if there is something that appears. Let's try an example. So with the article, we've seen that the compounds that are that we want to study is the para-bromobenzaldehyde. No. 3, 4. So we can use, if your compound is already known and is commercial, you can find the compound description in an experimental database. For example, PubChem lists like 100 millions of compounds, and you can have the safety and hazards informations, and you can have a 2D depiction, and you can have also a 3D conformation that are it's not really a quantum mechanics optimization, it's a molecular mechanics. That means that it's more or less like if you you say, okay, this carbon is sp2, 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 converge to the most reliable structure, and it will adopt typical bond lengths and angles due to the chemical environment that is defined. Okay, so this is really cheap. You can find a molecular optimization even in Chem 3D, for example, in the Chem Office, or many other programs. It can be quite interesting to use this as a first information, as a something that you can use as a starting geometry. Okay, so for example, here we don't have much a choice. We could do a rotation of the aldehyde, but since the phenyl is not substituted in the ortho near the aldehyde, there is no difference. Okay, so you can download the 3D information with the SDS file. You have all JSONs, XML, and other file programs. Those are XML and JSON are if you display, you will see that there are dictionaries. So you have some it's the same information, but there is like XML is a little bit like HTML. You have some opening information, closing information, and so it's easier for a program to read these files. The SDF is the most basic one, almost, and you have some information that are here, the atoms in 3D coordinates, and here you have the bonds. So you could give to Gaussian the information of the atomic position in 3D and the bonds, or not. So we'll discuss that. So I will download the SDF. Let's see. However, the SDF, you have too much information. you have, for example, here you have partial charges in the pubchem. You have more information that is needed. And in quantum chemistry, there is quite a lot of file formats. So to ease the conversion, you have a program that is called OpenBabel. OpenBabel is a program to transform to I don't want the docs, I want the first. Okay, it's an open source chemistry toolbox that read, write and convert between file formats. There is a Gaussian version or there is a Linux version. Okay, so I will use the conversion of this file and convert it to a more simple, even simpler file that is called the XYZ. So here you are looking at a Linux terminal. You can do scientific computing with Windows, but usually the all calculators are in Linux in order to save RAM memory, for example, because the terminal and the Linux are use much less memory and leave more CPU power for the computation, and they are quite they are much more stable in time. That means that they usually don't need to reboot. You can leave a Linux computer working for several days and months without any reboot. So the Master 1 students that were in Nantes last year already used a little bit of Linux knowledge in order to do their projects. Here we are in the Moltec Anjou cluster calculation facility. It's in the lab, and normally you have access to this computer directly from your classroom. There is two computers that are designed to leave you this access and to follow your projects. This year I will be your intermediate, your interface, and I will launch your calculations. So it will be more a demonstration than a fully practical approach. We used a user that is SHIM STG1. That means SHIM Internship 1. And there is already calculation made by the Lumomat. So we will go to this directory and we will create your directory for this year. Okay. So Bolton means all calculations for the Honest-Bolton paper. I will do a directory for our compound. So I think it's BR C6, if I recall correctly. Mono for a monomer. this is XMOBA X term. So at home I have a Windows, and this program allows me to use graphical terminals of Linux without having all my OS as a Linux at home. And you have in the right part of the screen, you see that there is a terminal with the Linux commands in Bash. Into the left part, you have an FTP access, so you can transfer and download components easily.
And what is the name of the program in order to
MOBA, it's MOBA Xterm. Here. And it's free.
Okay.
OpenBabel takes an input. So you say my input. Okay, so this is the keyword to say input type, and you give him the input file. You want in an output, you want a XYZ, and this will be the answer. So in the XYZ format, you only have the XYZ information. That means that you lose the interaction, that means the bonding. And you can launch Gaussian with the bonding, or you can leave quantum chemistry free to find what could be the best bonding approach. And I advise you that at first you start with leaving the quantum chemistry assign if it's a single bond, a conjugated one, or a double bond. You just put the atom in a reasonable structure. So we have an SD file, and in 3D it seems to be correct. Okay, so we will not give him the bonding between the atoms, but since you have an oxygen here that will be alone and near a carbon, quantum mechanics will probably optimize to a double bond, okay, and leave the hydrogen bonded to the carbon, and so on. So tier 4, we will only give the atom in 3 dimensions. So I will just copy, for example, what I've done recently that is interesting. We have so I'm looking for already done inputs. Okay. So I've taken an already calculated compound, and I will change the 3D coordinates. So the 3D coordinates is at the end of the information, after the parameters. And one thing that is important when you will be doing your own input is that after the last atom there is a blank line. The computer will read each line until there is a blank line, and for Gaussian, for this program, it means this is the end of this section. If you don't have a blank line, he will be stuck at, okay, I'm waiting for a new line because there is still I didn't have the order to say that the geometry is done, and he is waiting for an interactive approach where you can put atoms interactively, so it will crash. So leave a blank line after the coordinates. 0 and 1 is the charge and spin multiplicity. So here we have an already we have a developed structure that means that all electrons are in pairs. Okay, we have non-bonding electrons, but there is like 3 doublets here, 2 here, and all other atoms have the all the electrons, valence shell electrons paired. Okay, so we will start with a singlet state. That means the spin multiplicity is 2s plus 1, and if you have a multiplicity of 1, that means that you have no spin. Your total spin is 0, or all your up electrons, alpha electrons, are compensated by beta electrons in all orbitals. Okay, and the first part and the first lines are computational parameters. We've talked about the functional, so here I'm using a PBE1 PBE. PBE1 PBE here is like the B3 leap, but slightly better for excited states. If you want geometry, if you want energies, total energies, B3 leap, it's reliable. If you want excited states, absorption and emission, PBE1 PBE is good. It's not the best, but it's quite good, and an average in a generalistic hybrid orbital. Hybrid is because there is some DFT and there is a part of the Hartree-Fock. That means that pure DFT functionals tends to exaggerate the LUMO energies, so they are quite bad in terms of excitations, and Hartree-Fock is the opposite. And mixing the two, you have a compensation of error. That means that you have quite reliable results and precise results because you compensate the error of the Hartree-Fock and the DFT.
Excuse me.
Yeah.
Does the PBE do the same thing as B3 leap, or do we have to run both calculations, B3 leap and PBE, if we want energy and also excited states?
So, if you want excited states and you like to have some energy but it's not crucial, you can use PB for everything. If you want to do some reactivity and you know that the answer will be a little bit different, maybe you will need to do a B3 leap with optimization and frequencies for your reactivity, and do a TD-DFT in PBE 1 PBE to have the excited states. But like I said Tuesday, you need to compute the optimization with the PBE. So that means that you need to do the work twice, once in B3 leap and once in PBE 1. Okay, PBE 1 PBE is also called PBE 0, by the way. But I don't want to lose you in terms, okay? But you need to choose more or less what are your goals. If you want to do energy thermochemistry, geometry and thermochemistry, B3 is perfect. If you want specifically excited states, you can choose PBE 1 PBE. And if you have a special compound, for example, if you know that you have a problematic compound with a especially large interaction at long distance, maybe you need to adapt your parameters, and we will talk about it depending on what you choose. For the bromobenzaldehyde, we want the absorption and emission. I will start with this.
Okay, and what we want to obtain when we say that we want to obtain energies or excitation levels, what it will provide us then if we get this, or energies or excitation levels, what we can do with them.
Okay, so the question is, what do we do with the logs will be the objective of the next session. Okay, but for now,
we can choose between energies and the excited state.
Exactly. So you have your scientific problem. You know that either you only need to compare, for example, the free energies, okay? So you need the Gibbs free energies to compare the thermochemical stability between two compounds or products and reactants, for example, or you need to search for the geometries, for the energy potential energy surface, and you need to compute a transition state. If you want only that, B3 leap, it's okay. It's fine. It's really effective. If you want absorption spectra, emission spectra, instead of B3 leap, you use PBE 1 PBE. Okay? So you already know what kind of information you need depending on your scientific problem. And maybe your question was, how can we tell the computer what information we're looking for? And this is this keyword. So here we have an OPT keyword. So it's the kind of job that you need. So here, job type, OPT for optimization, FREC for frequencies, and TD for time-dependent DFT. So that means that here, if you put OPT, it will optimize the geometry of what you're giving him. And it will give you HOMO, LUMO, energy electrons, and total energy. If you want to do the frequency calculation to characterize, you need to give him the FREC keyword. If you want him to do both, that means that you start with an optimization, then you do the frequency, you give him both. If you want if you want excited states, you will give him the TD information.
So if I want to obtain absorption and emission spectra, I have to choose TD?
Yes, however, This is what we've commented last time. To do a correct absorption spectra, you need to know the converged and relaxed ground state. So your first step will always be an optimization. So we will do the calculations in more than one input. I use several files. You can put your different step in one input, but I prefer several files, and I will explain to you why later on. But for me, I will start with doing the optimization. He will search for the geometry of the ground state, and I will give him later in another file the information. So this is the ground state. Now calculate the absorption spectra, please. Let's see. This is a small molecule. We will be doing some dimers. Okay, so let's see if I do. No. Okay, if we launch a lot of calculations, let's start with something that is efficient. So we have PBE1, PBE, the functional. Here a basis set, it's quite large. With the Popple basis set, you have to see how many kinds of valence shell you want. So I want a triple zeta. That means that all my electrons in the valence states can be described by 3 different kind of functions. So it costs more. Each more you put the of 1 here, it costs more. Plus, that means that you had some diffuse functions. So there is mathematical functions that allow the electron of each atom to fill the space in a larger or to fill a larger space, and that will mean that if you have an electron that moves away from his initial states, he will have more ease to do so. And we have also in mind that we want to understand some intermolecular interactions. So I would like to add diffuse function to allow the wave function to fill each other at larger distances. After the G that means it's a Gaussian function. So it's a mathematical approximation that simplifies the real atomic orbitals that are Slater functions. And here in the parentheses there are the polarizations. That means that the electrons, instead of being in a pure p orbital, they can be in a p orbital with some d characters. That means that they are polarized. That means that, for example, if you take here a simple H2 molecule, H2, you have electrons in 1s orbital, but the 1s in the molecule is not purely spherical, because the second nucleus will deform, will polarize, and change the form of your orbital. So instead of having a pure s function, you will have some p character that will break your spherical symmetry. That is why, for example, for the p orbitals of the carbon, we will add some d orbitals some f orbitals, and to the s orbital of the hydrogen, I will give him the if he wants to use p characters and d orbitals. That does not mean that we move electrons of the hydrogen to a real p orbital and d orbital. That means that we use a fictive d orbital and p orbital that will just be used as a tool to transform the form of your pure atomic orbitals. The atomic orbitals are solutions of the equation, Schrödinger equation, but for one atom only. So if you need to the electronic density will transform depending on the surrounding, and those are functions that are mandatory to have reliable answers. So I tell him to do an optimization. Then you have more specific keywords. Direct is to tell Gaussian to use, if possible, all the interactions, all the integrals are computed in the RAM and not in the disk. So you will have it's a little bit more efficient in terms of computational power cost. GFprint is a keyword that we need to generate the pictures of the orbital if we use our program, my program. If you use other program, maybe you don't need it. And pop is just to say that you do a population analysis, bonding analysis, atomic charge analysis. So this line with the slash the hashtag p is a line of computational method, and you must give him the memory size, the RAM memory that he can use. So he will use 2 gigabytes of memory. He will use 4 processors. So depending on your computer, depending on how much processors you have, so I've chosen 4 so that I can launch quite a lot of calculations. I can do more, but for example, if I use 8, the calculation will not go twice faster, because when one processor is calculating, sometimes he is waiting for the answer of another processor, so there is waiting time. And Gaussian is not really super efficient. If you put 20, it will not be 5 times faster. It will be like 3 times faster. So if you launch 5 calculations of 4 processors, it's more efficient than a series, a list of 20 processors calculations. But if you want the answer rapidly, if you put more processors, it will go faster. And the CHK is an information of the binary file. The program will compute and write the data in a binary file that is understandable by the machine and not by us. And he will write also a log file that is in text for us. But the main computation will be done in a .chk, a checkpoint file. This checkpoint file allows us to stop the calculation and restart the calculations. So here, if we do that, you will have an optimization. But imagine that we want also frequencies and TD-DFT. Therefore, we have an frequency input and a TD input. What I like to do is reusing generic files. So, for example, here we have a file that you don't have the same information. You have a CHK that tells that the CHK will be called frec, the number of processors. So let's say it's 4. Okay. The memory, here it's 3 gigabytes. Okay. Frequency, use a little bit more memory. We tell him it's a frequency calculation. We tell him it's a PBE1 PBE calculation. And we tell him here to go and check the basis set in the checkpoint file. So that means that Gaussian can already read some information in a previous checkpoint file. So if we give him the opt.chk, we copy the opt.chk in the frec.chk, it will start by reading what you have in this file. And it will read the basis set. So you are sure by this way that he will use the same basis set. You can guess the initial wave function. So that means that the first wave function will be already optimized because it's already written in the checkpoint file. And you can check the geometry. And here you have geom check or geom all check. And that means that all check, he will also get the charge and multiplicity. So he will take from the CHK the geometry, the charge, the multiplicity, the wave function, and the basis set. So that means that this input file, frec.input, can adapt on all your compounds because it only depends on your input or opt.chk. And the same for the TD-DFT. For the TD-DFT, you have the CHK that is called now TD. We use the same number of processors, it's easier. We have a memory of 3 gigabytes. It's more than the OPT, and the same as the TD-DFT, the frequency. Same approach, we give him the functional. We ask him to search for the basis set in the already CHK file, to get the initial wave function in the CHK file, to get the geometry in the CHK file, and by the way, that means that he will already start with the converged, the final geometry of the CHK, not the initial one. And you give him here some information. Here, in TD, you have you must specify the number of excited states that you want, and you can also search for triplet states, for example. And here, since we suspect a phosphorescence, we need a TD-DFT with the triplet. So I will copy the TD input to create a triplet. Holidays, commercials, perfect. So we will have two kinds of excited state calculations. We will have the time dependent and the triplet time dependent. So here, instead of just time dependent 15, I need to tell him to do a triplet state. Maybe we can compute a little bit less. No, 15 also. So we'll see. So here we have the input files, and to launch the calculation, we need to ask the cluster to do the calculation in some order. This is the file that we submit to our scheduler. The scheduler is a program that will run calculation after the other. For example, we have here 4 projects. Okay, we have 3, 3, 3, 3, and our 2 Ukrainian guys. We have 4 scientific projects. We have the Honors Bolton project, so we have 5 projects. Each of you will have probably more than 1 molecule to compute. So we'll have at least 10, 15, 20 molecules to compute. To do so,
why we have 15, 16 molecules?
just that depending on your problem, but for example, we have the optimization, the frequency, the time dependent for all your molecules, and for some scientific problems, I know that usually there is not just one molecule to compute. You want to compare two compounds because you have a substituent effect or so on. Okay, so that means that you have much more than one molecule to compound, more than one calculations to do. So we have a list of calculations, and we cannot wait for them to finish. We have a scheduler that will launch them when the the one that are running are finished.
Yes, why by another?
Yeah. So here, so this is the bash script, okay? So it's a little bit more complex, but not so much. PBS N is the name of your compound that only appears in the stats, okay? Even if you use the same name, it doesn't matter. Here, the ppn1 here is the number of processor. It should be the same as in the input files. We have here something that is a right shell. It will start with putting the date. You will have then a CD that it will go to the directory of your input. It will launch the command g09 opt.input. That means that it will start to run Gaussian for this OPT. Then I've added a quality control. I check, so when this command is finished, it reads the next line, and it will try to see if there is a normal termination in the log file. That means if the optimization went correctly, it can go on. If not, exit. Exit, that means that it will move away. So here you have an SSH. You don't need those. Those line is usually it send a mail, but we didn't define a mail here. Okay. So if the OPT is bad, it will stop the calculation with this exit. If not, it will copy the checkpoint file of the optimization to the TD, and then it will run the TD. Then, and I need to change it, for example, I need him to calculate the TDT to do the triplet state, and then he will do the frequency. Okay, so I will download those files. And give you an example so you can prepare your own inputs. If you have a Windows, so you can all work on that. It's a text file, so you can open your file with a WordPad, for example, or a simple text editor. Up, I put them in the chat. Model. Okay, so in the chat, I've just downloaded the input file. You need to modify the opt.enp with your own 3D structure and modify your job with your name. And so we will create, you will send me back the corresponding inputs. Okay, it can be either just the file, or a zip of all your compounds, and you can start by working on your input files. Do you have any question?
Actually, I feel actually lost because like I understand the overall idea, but I don't know how to do it in real life, because like
Perfect.
you said that we have to make this input files, but actually I don't understand maybe 90% of operations you are doing in terminal.
No, it's clearly because since it's a demonstration, it's really hard to it's like when somebody explains to you how to use a computer and you don't use it. That is why I need you to try, and you will tell me I'm stuck. What do I do? Okay, and so you will start again every process, and you will better understand the second time. Okay, so the first operation is to get the 3D coordinates. If your compound is known and you have here pubchem, it's easier. If it's not known, you will have to draw your compound and will.
Can I use ChemDraw in order to get a 3D formula?
Uh,
I have a formula and I want to get.
Okay.
3D.
ChemDraw, I'm not sure that ChemDraw can save in that mol. You have a mol file. Oh, so let me. I have ChemDraw.
But you said that we can use some program to change.
Yes.
The extension.
So here in ChemDraw,
Because actually ChemDraw says that it can't provide a name for my structure. I don't know why, but
okay. So here, if I save as, yes, you can use, if you have a ChemDraw, you can use an MDL mol file, for example. Okay, so you use, for example, a mol file or an SDF file. But I think that the best is to have a 3D property, that to generate a 3D conformer. So it's better if you have a Chem3D.
okay. It's in the pack, I suppose, yeah.
I
So
suppose.
I can do that and generate 3D, and then I have to save a 3D copy, yeah.
Yeah. So Chem3D. Yep, Chem3D. How does it work?
I have Chem3D.
Can you just copy paste? Yep. So in Chem3D you can copy in ChemDraw and do a Chem3D. You can even do a molecular mechanics optimization. So it's, for example, MMF 94, and it's a minimization. Okay, but
so I have to make a minimization by MF94.
Yeah, if you want, if you think that your drawing in 3D is quite strange, you can try to do an MMF 94 optimization. Okay, for me,
what I'll get with that, like when I'll do this optimization, what it gives me, this optimization.
it will, if you.
So I have a structure like.
Okay, if you see my screen, I have my structure. When I do the minimization, look at the aldehyde position. See, it's fast. Huh? Okay, run up. The distance in the aldehyde CC bond slightly changed.
Yeah.
And that's all. So usually a molecular mechanics approach is a slightly better initial state for quantum mechanics than a pure drawing. Okay, and you save as SDS file.
SDF, yeah.
Yeah, and you download OpenBabel, and you for Windows, if you have a Windows, and you can convert your SDF file in .xyz.
With OpenBabel.
Yeah, and when you have your XYZ, you can edit the XYZ and the opt.enp and copy paste your atomic position in your input file, and you're almost done.
No, it's a bit better.
So I pause the recording.